Well, good morning, everyone. Welcome to the AIPG Lunch and Earn Seminar for February. I'm Aaron Johnson, the Executive Director of AIPG. And today we're going to be listening to Rick Cowles. Rick works for Stantec. He's got more than 30 years of experience in water and water supply management, working largely in aquifer storage and recovery wells, as well as doing some reclaimed water work. Rick went and got a bachelor's degree in geology at Mount Union College, where he was a Purple Raider, and then went on to Wright State University to get his master's degree, where he became a regular Raider. I can't comment on whether or not he's a fan of the Oakland Raiders, but it is my pleasure to welcome him here today. Rick, thank you for donating your time, energy, and effort to AIPG. I appreciate that very much. The floor is yours.
Well, thank you very much. That was a very nice introduction. I was not expecting that. I'm going to go ahead and turn my video off here so you're not looking at me, and we'll get started on the presentation. So appreciate everybody joining today. We're going to talk about the Lake Okeechobee Watershed Restoration Project, or LORP. And this is a project that is also part of the overall Everglades Restoration Project. So it's a very large project. It may be the largest of its kind. The ASR portion of this project may be the largest of its kind in the United States, if not the world. So we're going to be talking about aquifer storage and recovery. And essentially, just so everybody understands, what we're doing is we're taking water from the local rivers and canals, treating it, pumping it underground, storing it, and then recovering it back into the same watershed. And we'll talk about it in a little more detail in a minute. And I'll try to go through as these images come up, tell you what's going on. These are two drill rigs running simultaneously at one of our ASR well sites. The larger drill rig is constructing an Avon Park permeable zone ASR well that's about 1,450 feet deep. And then the smaller rig is constructing a upper Floridan aquifer ASR well that is about 850 feet. And at one point at the start of this project, we actually had 8 drill rigs operating at the same time. So it's a very big project, and we've just scratched the surface in terms of the construction of these wells. So a quick safety moment, since we're going to be talking about construction today, just if you're on a construction site, just be very aware. There's a lot of activities going on, equipment moving around. Stay away from the moving equipment. Make sure you have eye contact with whoever's operating that equipment so they know that you're there. Be aware of any kind of tripping hazards that might be around or anything above your head. And in this picture, there's a crane. If the crane is being operated, make sure you stay away from that crane, because anything can happen when heavy loads are being lifted. So just be very aware when you are on a job site, have your personal protective equipment on, hard hat, steel-toed boots, high visibility jacket, ear protection, eye protection, those kind of things. And if you're not familiar with the site, make sure you're being escorted. The image that you see here is at another ASR well site where we started working last fall. And this is a rig that's installing an Avon Park permeable zone ASR well. It's a SRAM drill rig. It's pretty impressive. All right, let's move on. So ASR program overview. So like I mentioned earlier, the ASR program is one of the largest in the world that's going on right now. And there's a lot of stakeholders. South Florida Water Management District is the primary stakeholder. That's who we work for. We also have cooperative funding with the Corps of Engineers. So they're splitting the funding on this about 50-50. And the funding right now, I think it's funded for $400 million with the ability to go to over $1 billion as this thing progresses. Didn't want to encumber all that funding right now because it's a progressive construction project. We also are working very closely with the USGS, United States Geological Survey, Gulf Coast, Florida Gulf Coast University, and many consultants. And I want to just mention a couple of them. David Pine, who has his own ASR company. He's one of the initial founders, you might say, of ASR, wrote the book on ASR. We have Collier Geophysical that has done some surface geophysics seismic surveys for us, and we're going to be working with them on some fracture trace analysis. Another company called Respect that has helped on the construction of these wells, as well as Earthology, who has also helped on the construction of the wells. And there's a number of other consultants that are outside of Stantec's work on these projects. So go on here. So here's an overview of the ASR program. Like I mentioned on the opening slide, these ASR wells are going to take surface water from the canals that flow in, canals and rivers that flow into Lake Okeechobee during the wet season when there's excess water. We're going to treat it to drinking water standards, store it underground until the dry season arrives, and then we're going to recover it. The well fields, there's going to be, right now there's 10 different sites, but it's going to be narrowed down to probably 5 or 6 sites in the end. And we'll talk about some of that assessment work that's narrowing it down. But each site will have 10 ASR wells on it. And these ASR wells will have a well completed in the Upper Florida Aquifer, the UFA, and a well completed in the APPZ, Avon Park Permeable Zone. Those 2 wells are considered one well pair. So there'll be 5 well pairs with these wells, each well having a UFA and APPZ well. Each ASR well will be capable, our goal is to be capable of receiving 3,500 gallons per minute or 5 MGD, and then recovering 3,500 gallons per minute or 5 MGD. So the total well, and then each well field will have a total capacity of 50 MGD. So we'll have a 50 MGD treatment plant at 5 or 6 well fields. The total capacity will be 275 million gallons per day. So let's go on. We're going to be focusing today on the C38 North and South site. This is where we put the first 2 well pairs, 2 at the north, 2 at the south, and then L63 North when we get to the construction discussion. We're also going to be talking about these other sites in terms of assessment, continuous cores, other things that are going on. And then we'll talk at the end a little bit about the treatment process that's being evaluated right now. So an overview of kind of what's going on, why we're doing this. I think most of you have probably heard of the Everglades and the restoration of the Everglades through, initially the Everglades drained, a lot of the Florida Peninsula starting north of Orlando, and then that water flowed through Lake Okeechobee and then was dispersed out the southern part of the state through the Everglades. Then later, this water was channelized, put into canals to create land for agricultural uses, for development, those kind of things. And that reduced the amount of water coming through the Everglades and being discharged significantly, which harmed the environment quite a bit. So right now there's a big program that's been ongoing for many years to restore the Everglades. So as part of that restoration, we got the ASR project that is going to help restore lake levels, but also the Corps of Engineers and South Florida Water Management District is removing a number of these canals that had redirected that water so that the water will again flow down through the Everglades. So the purpose of the LORT project, again, part of the Comprehensive Everglades plan, is to improve water levels in Lake Okeechobee. And there may be some on the phone that have heard about the algae blooms that have occurred in the past during the dry season in Lake Okeechobee. Well, the ASR wells are meant to restore or stabilize those lake levels during the dry season. So we pull the water out during the wet season, discharge it back into the canals and rivers during the dry season, and keep those water levels up. It's also been shown that the aquifer removes a lot of the nutrients, and a lot of the nutrients are going to be removed through the treatment process as well. So the water that we're recovering will be very low in nutrients, which is also going to help. The program also will improve the quality and the timing of discharges to the St. Lucie, which is over here on the east coast, and the Caloosahatchee River or estuary over here on the west coast. So during the wet season, there's a lot of fresh water that are discharged out into the Gulf and into the Atlantic Ocean that damages corals and other things. And it increases the spatial extent of the wetlands, and that just means we're expanding the wetlands. Improves water quality Lake O, which I just said, and then also improves water quality to legal water users in the area. So very multifaceted benefit for doing these programs. So what work has been going on and where are we at? So we're going to talk about the hydrogeologic assessments that have been ongoing, and this is the first phase. Are these locations suitable for the development of 50 million gallons of water per day? Do we have enough space for the treatment plant? Do we have enough space for the For all the ASR wells, is the canal or river deep enough that we can pull 50 MGD out of it and then it can be put back in, because most of these canals and rivers are also used for boating. And then what's the water quality like in the aquifers? So to answer some of those questions, we also advanced we have continuous core holes. We've advanced 4 of them. There's a 5th one that's still coming up. But these continuous core holes are 2,000 feet deep, and we start collecting cores at 500 feet, which is a confining unit. So we have continuous core from 500 to 2,000 feet. We've also conducted a proof of concept or a pilot test for some treatment technologies. We'll talk a little bit about that later. There's a great deal of permitting going on. The major permit is the Florida Department of Environmental Protection underground injection control permit. And that's a permit that underground injection control is a permitting requirement for all injection wells. That's a federal requirement. The state of Florida manages that program themselves, but there's a lot of permitting through that. So every single well we install has a UIC permit. Oops, too far. C38 North and South, we have completed the design construction of the first 4 wells, or the first 2 well pairs, and we anticipate we're going to be going out to bid in another month, 2 months from now, for the second set of wells at the south site, which is pictured right here. And before I go on, since I mentioned this picture, this is the C38 south site. ASR wells are in this area, and you see one of the drill rigs. That's the APPZ drill rig. This is an APPZ monitoring well drill rig. We got another well up in this area. So it's a large site just for the first 2 wells. At the L63 North site, we're under construction right now. We should be finished with that late summer. And then we'll be constructing the second set of wells at the L63 North site, second set of ASR wells in late 2024. There's a groundwater model that's being prepared, and we're getting close to finishing that up. We just are just going to be starting a fracture trend or trace analysis of the area, and it's going to be a fairly large evaluation. We have a lot of detail from our borings and other people's borings, plus the seismic. So we want to understand where the water's flowing, what's the prominent flow directions out here and with these fractures, and can we predict where these fractures are so we can take advantage of that. And then we're in the process right now of designing a 10 MGD demonstration plant, which will be used for the initial cycle testing at the C38 South site sometime in 2026. And that's sucker's going right up here on this site. So once cycle testing is complete, this program is going to move forward quickly. The state Corps of Engineers, all the stakeholders want to have these ASR wells in and the treatment plants in as quickly as possible. So as soon as we can demonstrate that everything is feasible, then we're going to be cut loose and we're going to be constructing wells and designing and building plants on a fairly fast pace, and we already are. All right, so ASR well field assessment activities. So the first step is the hydrogeologic site assessment, which involves reviewing of published and unpublished data. And you say, how do you get unpublished data? Well, you go to the regulatory agencies and dig through their files and see what they have. Now, that isn't as big a deal as it used to be, because most of this data is now put online. So it's much easier to find than it was 15, 20 years ago when I was doing this kind of work. So, but we still look for unpublished information. And then from that, we develop a conceptual hydrogeologic model. We prepare cross sections, including the hydraulic data that we can find on any wells that have been constructed in the area, as well as water quality, specifically TDS, because TDS is kind of the main driver for us. We identify flow zones, which essentially are the storage zones within the aquifers, develop conceptual ASR and monitoring well designs, and then we present that information to both South Florida Water Management District and Florida Department of Environmental Protection in a pre-application meeting to make sure that we don't have any issues that would eliminate a site from being permitted. And then from there, we develop drawings where we lay out the footprint of a plant and the well field and make sure everything fits. So right now, we have finished our assessments of the C38 North and South, where we've constructed our first wells, L63 North, C59, L63 South, and C40, C41. So we're just, and these reports are just now going into review. So we're almost done with all the assessment activities. All right, so quick geologic section, which I'm sure everybody on the phone was just waiting to see. But this is a geologic column prepared from the data we've collected from the C38 North and C38 site along the Kissimmee River. Now, the Kissimmee River is the primary river coming into Lake Okeechobee. It's very large, has a lot of water, and that's one of the reasons we have two sites on it, because we can put two 50 MGD ASR systems on that river, if not even more. The base of the Hawthorne, which is a confining unit right up here, goes down to around 200 feet. And then below that is our first flow zone, the upper Florida and Aquifer, which includes both the Swanee limestone and the very top of the Ocala. These are defined by index fossils. And I'm not going to go into the index fossil names because I can't pronounce them, but they are for the Ocala, it's a foram. And for the Swanee, it's just, my mind just went blank. But it's a larger fossil of a bivalve. And dang, if I can't forget, it's so common I can't remember. The Avon Park permeable zone down here is two intervals. There's an upper Avon Park permeable zone and a lower Avon Park permeable zone, both very, very productive. They're separated by a middle semi-confining unit. We are concentrating on that upper APPZ because the water quality in the lower APPZ, TDS goes up very high. It approaches 10,000 milligrams per liter. So like I said, we identify those through index fossils, organic layers, unconformities. There's unconformities between almost every one of these units. Geologic descriptions that we make ourselves in the field or looking at the geologic descriptions in other wells in the area. Geophysical logs, and the geophysical logs are really, really important. And in fact, what we've done is gone in and taken the historical geophysical logs, the LAS files, and we have replotted them. And in many cases, the LAS files are the only thing on file. So we've actually plotted our own geophysical logs. And so let's see what that means. So here's two examples of some geophysical logs. We got the gamma over here on the left, along with a caliper log. This is the caliper, this is the gamma. And then over here on the right, we have a dual induction log right through here, and then gamma and spontaneous potential. So what we have found, and this is extremely consistent between sites around the northern part of Lake Okeechobee over to the eastern part of Lake Okeechobee, that the gamma signature is consistent when we get to the bottom of the Hawthorne and the top of the Swanee. There's an unconformity right there, and there's a concentration of phosphate nodules. So we get a big kick right here in that gamma signature. The gamma is picking up the natural gamma radiation in the formation, and clays tend to have a higher gamma radiation signature, and phosphate has a very high gamma signature. So this break right here in every instance has been the top of the Swanee. Over at the dual induction, as we get into the top of the Avon Park, we see a very smooth dual induction curve. And actually, if we extended this, it would actually bow out. We call it a belly. And then as that belly comes back in, we get this very erratic signature indicating a lot of fractures. And the Avon Park is dominated by fractures. And then as we go into that middle semi-confining unit, it's less fractures, a little more consistent. And then down below it, we go into the lower APPZ, and there's more fractures down here. And because we're not targeting that lower zone, I don't have as much of a complete geophysical log to show you, but you can see these signatures popping in. And when we look at some cross sections, you'll see how those look. So cross sections, there we go. So we've generated or created 10 cross sections through the north of Lake Okeechobee, actually wrapping around, it looks like about 3/4 of the lake through all of our sites, and then actually out into the region a little bit to look at the larger regional conditions around our well field. So we have C40, C41, C40, C38 north and south right in here, L63 north, C59, L63 south. And I'm sure you guys have memorized all those locations, but they're all covered with these cross sections. And here's one of the cross sections. This is cross section produced from our L63 north site. Here's that gamma signature, top of the upper Florida and Aquifer, which is made up again of the Swanee and the upper portion of the Ocala. You see coming through right here. And then here is that Avon Park permeable zone, the upper part of the Avon Park, the middle confining unit, the lower part of the Avon Park permeable zone showing right here. And you can trace that all the way across. And this particular boring actually went down into a lower unit called within the lower Florida aquifer called the Oldsmar, and there's another float zone down there, but the water quality is very poor. So we're not targeting that. So enough on the assessment. Let's look at something else. Once we finish the assessment work, the next step is to go out and actually physically examine these sites. So the district developed a continuous core program where they being us advanced 5 continuous cores, and actually we've completed 4 of them, and the 5th one will be scheduled sometime in the future. But what I'm showing you on this picture is not only the continuous core rig, but one of the things we do because we have so many stakeholders is periodically there'll be a VIP meeting at the site where we bring Corps of Engineers, South Florida Water Management District, county commissioners, whoever else needs to be updated on the progress of these projects. And so this was this picture over on the left shows, I think the general from one of the generals from the Corps came out along with his staff. And then a lot of these people over in this area is the district staff. And then we had other representatives from the county, just showing them what was going on and keeping them informed into the progress of this project. So back to our map. Like I said before, we're advancing these continuous cores down to 2,000 feet and start coring at 500 feet. The 500-foot depth keeps us in the Hawthorne, which is that upper confining unit. So we're not targeting that for a storage zone, but we want to collect a little bit of that so we don't miss the contact between at the upper Florida between the Hawthorne and the Swanee. So we start at 500 feet, go down to 2,000, and currently we have collected well over a mile of core. That's a lot of core. We run packer tests every 30 feet once we get into the Swanee. And so we'll core for 30 feet, pull everything out, run a packer test, off bottom packer. So we'll test that 30-foot interval and then core again. And we'll collect water quality information. We'll send data or samples out for isotope analysis so we can get an idea of the age of the aquifer. So we can see if we're mixing because we also collect it during our pumping tests. And then we also do what's called specific capacity tests, which is a short-term pumping test where we look at the relative permeability of the aquifers as we're advancing those cores. We run geophysical logs through the entire length of the core hole, and then optical borehole imaging logs, which it's a very highly detailed optical image of the borehole, and you can see fractures and bedding planes and things like that. And USGS runs the optical borehole imaging tool. And then core samples are sent to Mineralogy Inc. for scanning electron microscope analysis, thin section preparation and analysis, X-ray diffraction, and then isotope analysis or metal analysis within the core material itself. So here's our sites: C38 South, L63 North, C59, L63 South are complete. And then we're gonna, the next one be at C41. Here's some pictures of the cores. This is the Hawthorne, very distinct greenish gray clay. So it's pretty distinctive in terms of when you're in this and when you leave it, you start getting into these little limestone layers as you're getting toward the bottom of it. This is the contact between the base of the Hawthorne. You see all these rip-up clasts and stuff as you're getting close to that unconformity. And then this is the top of the Swanee that has oyster shells in it. That's that silly little word I couldn't remember a minute ago. So oyster shells are very distinctive of this formation, and that's where a lot of the permeability comes, is from these large cells. And then in the case of this one, this is at the L63 North site. The top of the Ocala is at 708.5 feet. So Swanee's fairly thin, came in about 700 feet. So we only have a little over 8 foot of it, maybe 10 foot of it. And then we go into the Ocala and there's this buff limestone. Here's more of that Ocala, very fine grained, silty, buff limestone, very friable, it tends to fall apart. And then we go, once we pass through the Ocala, we get into the Avon Park zone. And actually we hit the Avon Park formation first, which is about 1,250 feet at this site. And then the APPZ here is at 1,300 feet. And you can see how the material is breaking up, and this is a dolostone, very hard, very brittle dolostone. It cores very slowly, but most of the porosity in the Avon Park permeable zone is through the fractures that occur here. In the upper Floridan, it's the porosity is intergranular, so it's between the grains. So two different types of porosity that we're dealing with, and for our two storage zones. And then below the Avon Park, we go into the Old Small, which is part of the lower Floridan aquifer, and we get into evaporites. And this is anhydrite evaporites, very pretty, very thick sequences, but not very permeable. We also ran into an ash layer at 1,466 feet, so fairly deep. And when we were in the field, we identified it as a silica layer. So remember, we're in limestones. So carbonate, all at once we're into a silica layer. Well, where the heck did this come from? So we just noted it. Well, these samples were sent over to Florida Gulf Coast University, and they initially identified this as an impact crater up at Chesapeake Bay. But after further analysis, they determined that the grains were not correct. The quartz grains in here were not correct for an impact crater. And it turns out that it's more of a volcanic event that occurred in the Caribbean. But at any event, this is the first time this has been identified in Florida. And it's so thin, we haven't seen it at any other of our sites. It's so thin, it'd probably easily be eroded away. But at least we have it here, and we know that it's part of the geologic record. So here's some of the analysis that's done on the cores. Like I said, thin section analysis, identifying the different forams and stuff that are in the cores themselves, and then the scanning electron microscope, pyrite. And pyrite's important because one of the concerns, or one of the keys out here for the success, is the mobilization of arsenic. And arsenic is frequently associated with pyrite, arsenopyrite. So we look for that, and we look for opportunities to minimize the opportunity to mobilize the pyrite. But you can see some of the dolomite crystals in here, and it's just very fascinating work that is being done by the core lab. All right, so here's some of the data that was collected from the L63 North core hole. So we have a specific capacity data. Like I said, we're collecting or running specific capacity tests every 30 feet, as well as collecting water quality data. So this is a graph showing the specific capacity. You can see there's just a little bit of a bump up here at the top once we're into the Swanee, and then it kind of goes down to practically nothing as we go through the middle confining unit of the Ocala, and then the upper Avon Park permeable zone, zone 1. You see a big kick, and then we go into the middle confining, that semi-confining unit, where it drops way down, and then a huge kick down in the lower zone. So the lower zone is actually more permeable than the upper zone, but the water quality down here, right here, goes to crap. So the TDS increases a lot. We still have an increase in TDS as we go into the APPZ, but it really increases in the lower APPZ. And then below the lower APPZ, we get fresh again. So very low TDS. And then as we move into the lower Floridan aquifer, TDS increases. And so we have that TDS, 10,000 milligrams per liter interface TDS at 1,870 feet. This zone is a concern for us because as we pump the upper Avon Park permeable zone, we can induce recharge upward or upconing. So we can upcone this water down here of poorer quality. So as we inject water into this upper APPZ, displace the high TDS water as we're recovering it, we have to be very careful that we don't move this water up to us in it, and it reduces our recovery efficiency. And the recovery efficiency is essentially if you put 10 million gallons of water in and you recover 10 millions of gallons of water without a water quality change, that's 100% recovery efficiency. So anything less than that, the efficiency goes down. So you're monitoring water quality as you recover to determine when you start bringing in native groundwater. And this is just a larger section view. It has all the geophysical logs. There's that very distinctive resistivity pattern through here. Also shows up in our sonic logs. And then I don't think the gamma is on here. Yeah, there's the gamma, and you can see the kick right up here. So we got our upper Floridan aquifer, we got our upper APPZ, lower APPZ, and then down here at the very bottom of our core hole, we're getting into that lower Floridan aquifer. Here's some images of the OBI, because I'm sure every one of you wanted to see these as soon as I mentioned OBI. So 700 to 740, this is in the Swanee right here, and the upper part of the Ocala Formation. You can see there's quite a bit of porosity in these this borehole through that interval. And so this is our main storage zone within the upper Floridan Aquifer. The 1300 to 1360 is the upper APPZ, the upper Avon Park permeable zone. And you can see the difference. We got a lot of fractures, maybe some dilution going on here, dissolution within the dolostones, creating a great deal of porosity. There are some fractures in the upper Floridan aquifer, but for the most part, the APPZ is all fracture flow because this is a dolostone. A dolostone is very dense, very low permeability, low porosity in the rock itself. So it's the flow between, or not between the grains, but it's a flow through the fractures that give us our primary porosity or permeability in the APPZ. All right, so let's talk about the design of these wells. So this is, again, an image of the C38 South site, a little closer up of the APPZ drill rig. They're big rigs. We're putting in big casings. We're going to look at that very shortly. But I wanted to point out this little guy right over here. And we're going to talk about this more when we get to the treatment plant. But this is a pilot study ASR well site. So it's called the Kissimmee River ASR well site. It's completed in the upper Floridan Aquifer. And this was the very first ASR well in this area used as a pilot program. There's a little treatment plant over there. And the results from this gave the district, South Florida Water Management District, the confidence to move forward with this program. It was very successful. So here's our two sites, C38 North, C38 South. They're a little over 7 miles apart, and the wells that have been installed there. So just to recap the ongoing construction, 50 MGD well fields, C38 North, South, and L63 North. Those are ongoing. Completed our first well pairs at L63 South or C38 South, L63 North, and we'll start the second well pair at C38 South probably midsummer. And at the L63 North site, we are in construction for both the APPZ and the UFA well. We anticipate being finished sometime mid this year, maybe late summer, and then starting the second well pair late fall. And you see how big some of the equipment is that is needed to drill these wells. And you'll see why here in a second. So data is king in the ASR program. So what we do is when we're constructing these wells, even though we've got continuous cores and we've done the hydrogeologic assessment, we're collecting cuttings every 10 feet. We're doing drill stem water quality and specific capacity tests every rod. We are also doing alignment tests, make sure everything's good, square and plumb. Geophysical logs, and this is the list of the logs. I won't go through them. We're collecting additional cores that are going out to core lab to look at mineralogy, porosity, permeability, those kind of things. We're doing packer tests to confirm flow zones and confinement, because we want to make sure that between the upper Floridan and the APPZ, we're not leaking water between the two. We're not affecting the two when we're pumping. We're doing pumping tests. And in those pumping tests, we're measuring the sand content and the silt density index. And those are important for the treatment plant. We don't want silt because these treatment plants are going to be membrane plants. And then we're doing aquifer performance tests, which we'll get into great detail in a minute. And then every week, we have a weekly report that goes into FDP UIC on all the activities that occurred the previous week for both the C38 North, C38 South, and L63 North. So there's 3 reports that go in each week. Sometimes those reports are 400, 500 pages long. So significant reporting required in this project. And then we got the 2 tree frogs that were hanging out on top of the monitoring ones. All right, so let's talk casings. For the UFA, we have a 52-inch pit casing. That's the very first casing that goes in. Blocks off the upper part of the unconsolidated material so it doesn't interfere with our drilling. Then we have a surface casing that's 42 inches. That's completed on top of the Hawthorne. And then we have a 26-inch fiberglass reinforced plastic casing. That is the final well casing. That's a picture of the bottom of that FRP casing. It's embedded with very coarse material, about 200 feet of it. And that helps hold the cement around that casing so it doesn't fall out. Over here, just before I get to these others, is one of the reaming barrels. I believe this is the 52-inch reaming barrel. So we've got the drill bits all stacked up here, increasing size from the bottom to up top. And then this is a stabilizer, helps keep that barrel centered in the hole so we don't head off we don't directional drill. Let's just put it that way. Everything's kept straight. For the APPZ well, our first casing is 62 inches, second case 52, casing's 52, third casing, this goes all the way to the top of the upper Florida aquifer, 42-inch, big casings going 700 feet deep or more. And then our final casing again is 26-inch. It's FRP, fiberglass reinforced plastic. And then we also construct dual zone monitoring wells, which has a monitoring interval in the upper Florida aquifer flow zone and a monitoring interval down in the APPZ. And it's completed with 36, 24, 16, and 6 5/8-inch FRP casing. Another picture of the FRP casing, 26-inch FRP casing is as big as you can get right now for water supply wells. And so it's impressive casing. It's threaded together, it screws together. You put Teflon tape around the bottom threads. That's what this white stuff is. And then that's torqued together. And we get a torque report on every single joint as this casing goes in the ground. So these are just the pictures or the images of the well construction for the APPZ and the UFA well at C38 South, same casings, but they're telescoping casings. I don't know if you got that feel from the previous slide, but the larger casings have a smaller casing, have a smaller casing, have a smaller casing, all the way down. Each one of these casings block off an aquifer or block off a confining unit and isolate our storage zone or our recovery interval from the other aquifers. That's an important takeaway on these constructions because you don't want leakage occurring between these different aquifers. Here's some of the data that's collected, and I'm not going to go into all of it because it gets a little bit tiresome to see everything. But this is just the TDS for the C38 South site, C38 North, and you can see how the TDS is very consistent through the upper Florida aquifer or the UFA up in here, the Ocala. And then when we hit the Avon Park permeable zone, we get a big kick in the TDS, just like you saw on the continuous core hole at L63 North. Specific capacity, same kind of thing. We get kind of a low specific capacity through the Ocala, except up in the Swanee, and it's kind of hard to tell because of the scale, but the biggest kick's up in the Swanee, and then down in the Avon Park again, huge kick in specific capacity. This is one of the images or the drawings we put together for each well, and actually this one is a little bit truncated because we include every single geophysical log on this, so it's an actual fairly wide image that we provide. But on these images, we have all the packer testing and all the cores that are collected. This jiggity line here, and actually this has a little bit of an overlap of something on it, so it's not as clear. But this jiggity line is the actual caliper log. So that's the way the borehole looks, all that. Same thing down here in the open borehole image, and you can see down here in the lower APPZ, because this one went a little deeper and then we back plugged it, but you can see how that lower APPZ has a lot of big fractures in it. Here's our gamma log. There's that big kick. So we got the upper Florida aquifer and then dual induction. So you get a little bit of kick in it too as you go from the Hawthorne into the upper Florida, and then down here is our APPZ again. You get that very distinctive look down there. So let's talk about once the well's constructed, what do we do? And this is a stainless steel riser. It's about 15 feet long, and this goes on top of the FRP casing. So that threads into the FRP casing, and this is what actually sticks above ground. One of the first things we do once the well is complete is we acidize that well. So for the C38 North and South, we pump 20,000 gallons of 32% hydrochloric acid into the upper Floridan ASR well and the APPZ ASR well. And we're going to look at some of the data from that. This is called a Larkin header. So this has our acid piping. It has our freshwater piping because we have to control that reaction, and has pressure gauges, a transducer on it because we want to make sure we don't blow anything off. So we have a lot of water sitting around so that we can dilute that acid and keep that pressure on that wellhead down. And we do not want to see that go above 60 psi. So here's some images, downhole images of the UFA well at C38 South. So this is a pre-acid video right here. You kind of see how the borehole is a little bit smooth. We got a little fracture over here. This is the post-acid video, same spot, 537. In fact, I think it's oriented about the same way. And you can see how that acid opened up that fracture. In fact, there's another one over here. Very, very effective in opening weak spots in the limestone and opening porosity. And we're going to look at the porosity here in just a second. Here's that same fracture now looking downhole. So you can see the fracture extending down the borehole here and how the acid opened it up. And notice that that fracture doesn't go past this bedding plane down here. So it's a localized fracture. It's in the upper part of the upper Florida aquifer, very localized, but very large. Here's some of the porosity, how it affected that. So here's the borehole after the well was drilled, fairly smooth walled borehole comparatively to the other side. But you can see how the acid opened up that porosity. So the capacity of this well increased substantially. We're going to look at those numbers. But the acid was very effective about taking away all of the material that was pushed into the aquifer during the drilling process and then opening up those pore spaces even more. And these little white things that are sticking out here are corals. So the coral is a little more resistive to the acid process, but the pores are opening up very nicely. And it looks like I got about 9 minutes left, so I'm doing pretty good. Just another picture a little deeper. So we're down to 560, and you can see it just looks like a sponge down here. Very, very satisfying for a hydrogeologist to see this kind of difference. Takeaway, if you ever work on a limestone aquifer or even a limestone sand aquifer, always acidize. You're going to open it up and do yourself some very good, have some very good results. This is just some images of some of the data that we collect. Over here on the left side is the SDI press. There's a little filter that goes in here. There's a pump right here. Water is pumped through this at a specific pressure, and silt density index is measured. It is dimensionless. It's just a number. But you want to keep it down below 3, and we'd like to even see it down below 1 when it's going into a membrane plant, because that silt will clog up a membrane very quickly. We also have YSI water quality probes. We have, these are also water quality probes that measure continuously. So these, you have to write down the information as you read it out on an instrument. These record it continuously throughout whatever test you're doing. There's the YSI sitting there again. This is a rosin sand tester. We want that sand to be down to 0 as well, because that's going to screw up a membrane plant. So we're always looking at those kind of things as we're developing these wells. And this is a pump and motor. We have a water level tape here. But something I failed to mention, and I meant to at the beginning, is all of these wells around Lake Okeechobee are flowing artesian. Okay, so the water levels on these wells are somewhere between 22, 25, 30 feet above ground surface. They're way up in the air. The only reason we have this water level tape here is we pumped this well and the water levels went below ground surface. So we have a manometer tube on it when the well's not being pumped, and then we use a water level tape to measure water levels when the well is being pumped. So here's some of the results from our acidation. So the first one here, and I can't see it because it's under this little header up here, but I think this one is the C38 South UFA well. But you can see the pre-acid specific capacity test that was done here. So we did a step drawdown test ahead of our acidation so we could measure the effectiveness of that acidation process. And you can see our specific capacity numbers running down through here. So 115 at a fairly low rate, about 600 gallons per minute. And then our design rate of 3,500 gallons per minute, we had a specific capacity of 32. Post-acid, we had at about 1,300 gallons per minute. We jumped up from 72 or 78, depending on which test you were looking at, to 500 and some. Tremendous increase. And then when we get to our design rate over here, we went from 32 to 246. And we actually pumped this well clear up to 6,000 gallons per minute with a specific capacity of 154. So our specific capacity at 6,000 was greater than our specific capacity pre-acid at 3,500. So very successful, huge increase in efficiency or specific capacity in this well after acidation. Same thing at the north site. It wasn't as dramatic, the increase, because the aquifer up there is a little more permeable. And this is, I believe, the APPZ, yeah, it says right there. So we went from 215 pre-acid to 537 specific capacity post-acid, 250% increase. Still a nice increase, huge benefit from that acid. And this must be the UFA wells, and similar increases at 1,300% increase for the UFA at the north side, south side, and 500% at the north side. But look at these specific capacity numbers for the north side, pathetic. And we're going to look at that a little bit. But we have the geology or the hydrogeology at the C38 north and south side within the UFA are completely different. And this came as a complete surprise to all of us. We didn't do a test boring at the north side. We only did our test boring, our continuous core at the south side. But it turns out that the UFA at the north side is not a producer. But we'll look at that here in a minute. So this is just kind of wrapping up the results from the acidation. So to keep moving along here, because I've got looks like about 4 minutes left and still got some stuff to do. Aquifer performance testing. The last thing we did after the wells were constructed is we did aquifer performance tests or pumping tests. And this is just a quick reminder of the zones that we're targeting: Upper Floridan, Upper APPZ. Both aquifers are flowing artesian. Map again of the two sites. We had 27 monitoring wells between the two sites. We used 60 transducers during our APT testing. So each monitoring well had 2 transducers, so we didn't need to worry too much about failures, even though we did have to replace some transducers. And the reason is we did 2 4-day tests, or 1 4-day test at the south side, 1 4-day test at the north side, and it actually turned into a 5-day test at the north side because we had the last test fail 3 days into it, so we had to rerun it. But that's a lot of 5-day tests. So we did a combined artesian test at both sites, both wells flowing naturally, a APPZ pumping test at both sites, a UFA pumping test at both sites, and then a combined pumping test at both sites, because that's really how these well fields or these ASR well fields are going to be operated during recovery. Both wells are going to be operated at the same time. We had 48 hours recovery between the tests, and then prior to starting all of these tests, we have a 30-day pre-test monitoring, so we could see what the groundwater level trends were ahead of the test, so we knew how we'd have to correct the data. So use Cooper, Jacob, Tice, Hontush, Jacob, Tice recovery, and then a USGS program for correcting some of the diurnal effects that we were seeing in the data to pull that out and make the data curves just a little bit smoother. So the data, the purpose of these APTs, and this is important, is to determine the hydraulic characteristics of the aquifer. So what is the transmissivity? What is the storativity? Is there leakage? Those kind of things. That data is going to go into a groundwater model, or is in a groundwater model that will be used to predict, do predictive simulation or scenarios associated with the injection bubble. What will the geometry of that bubble look like when we're injecting water in the UFA and the APPZ, and then predict the recovery of efficiency. So we're using also a density dependent portion on that model to look at recovery efficiencies and to identify the potential upconing between the aquifers. How is that going to change the water quality as we're pumping these wells? We're also using that to determine the spacing or confirm the spacing between all the ASR well pairs. Right now it's 1,000 feet. We think we're good. And the model is starting to support us in that assumption. So here's some of the corrected data. So the blue line is what it looked like before. This is a diurnal effect right here. This is actually tidal. It's only a couple tenths of a foot, but it's definitely in the data. And then we also had a barometric effect that was corrected as well. So this orange line is the corrected data. So you can see how it's smoothed it. You can't get everything out, but it smoothed it quite a bit. So APTs, here is a picture of one of the manometer tubes. This is about 25, 28 feet in the air. And when we started these tests, we had to use binoculars to kind of confirm to be able to measure the height. We had a measuring tape that went all the way up, and these girls, ladies down here are monitoring the water level changes as we start this test, one of these tests. Here are our flow rates. Pumping rates were determined both with an orifice system. So that's an orifice plate, which is a little smaller than the diameter of the pipe, as well as a flow meter. We're hanging our hats on the orifice numbers. more so than the flow meter, because the flow meter, the error between the orifice number and the flow meter became greater and greater as the pumping rate increased. So artesian at C38 South, we were pumping or flowing at 2,500 gallons per minute, over 3 million gallons a day, just flowing artesian head from the APPZ, and 1,500 gallons per minute, a little bit more from the UFA. So over 2 MGD from the UFA. And then during pumping, we pumped APPZ at about 5,200 and the UFA at about 4,500. And the lower pumping rate in the UFA was more related to the pump issue, not being able to, we only had about 30 feet of drawdown below ground surface, but the pump head couldn't get us up to 5,200. So real quick, it looks like it might be over time. So tell you what, I'm going to skip through this real quick and go to the treatment. So these are drawdown curves, and I just want to show you this one real quick. This is for the UFA well at C38 South, and 1,000 minutes into the test, and each test is 7,200 minutes long. So this is a logarithmic scale here. But notice how the drawdown actually started coming back up. So we had some recharge going on in the UFA, probably localized. If we pumped it longer, this might have started down on this curve again. But we're looking at transmissivities. Let me just go to the summation here of about 300,000 in the UFA, gallons per day per foot, or just under 1 million in the APPZ, gallons per day per foot. And here's our feet squared per day if you want to have your flow in little cubes or squares or something. All right, north site. And like I said before, the UFA well is not pumping as well. So here's the flow from the UFA well. Here's the flow from the APPZ well. Quite dramatic difference. But let's just go to the results, and the transmissivity for the north site, UFA 2,500 compared to almost 300,000. And the APPZ is twice as transmissive at the north side as the south side, running a little over 2 million gallons per day per foot. So treatment, proof of concept. The first thing we did was go out to the site at the Kissimmee site and set up a number of membranes. So we had polymeric and we had ceramic, and we also looked at just straight filtration with UV. So here's the existing ASR pilot program or pilot site that I was telling you about. Here's our C38 South site. We have an intake. It was a 5 MGD system. We had a pressurized filter and then UV going down into the well. Found out, and then that discharged down a cascade aerator to reoxygenate the water before it went back into the river. Worked very, very well. But what we found is that the tannin color in the river affected the UV significantly, and we busted our bacteria requirements. So UV was not going to be appropriate. We did try again with some different UV vessels just in case we could use a filtration system, but it turned out not to be practical. So it's going to end up being some kind of membrane treatment for the treatment plants, either polymeric or ceramic. And since we're moving fast, here is a footprint of the demonstration plant. This is a 10 MGD demonstration plant. We're going to split that 10 MGD between 2 polymeric skids and 1 ceramic skid. We're going to look at deoxygenation of the water as well before it goes into the wells. Here's the second set of wells that are going to be constructed here soon. Here's the first set down here, and that's to limit the mobilization of arsenic. And then we're also going to pull in this existing ASR well on the other side of the river through a directional drill. And I don't know if you noticed at the beginning of the talk that was 55 ASR wells, and you're going, how do you do that with well pairs? Well, there's your odd man out right there. That's the 55th well. So I'm just a little bit over time. That's the end of it. Any questions?
Hey, everyone, before we hop into questions, a couple of really quick housekeeping notes. If you're trying to get CEUs for the state of New York, Wendy's going to drop a link into the chat. You will have to complete that assessment and get 4 of the 5 questions correct to be able to receive your CEUs. That is a requirement for the New York State Education Department. You can take that as many times as you'd like, but it's only going to be open for about half an hour. So be sure that you hop in and take that. I see several questions in the chat, Rick. So what I thought I might do is reach out with those first, and then folks, you can put questions in the chat. We'll do questions at least for a few minutes here. The first one is from Ray Talkington and seconded by Tony Giunta. asking if PFAS is an issue with Teflon tape on the FRP, given the new EPA standard setting PFAS so low.
Good question. And the answer on that is no. All that those joints are encased in cement. But one of the things that we are looking at is PFAS in the Kissimmee River or in the canals. And that is more of a concern than on the well construction itself, because like I said, all of those joints and everything are encased. So we have a fairly significant sampling program ongoing right now. And things are looking pretty good. For the most part, the PFAS and PFOS concentrations are at or just below what the detector or the MCL is right now. It hasn't firmly been established, but we started sampling, I want to say in October. We're sampling through May right now, and we'll probably extend it beyond that because we want to get a full wet season, dry season sampling period. So we're sampling twice a week. We're considering sampling more frequently. We're also considering some sampling. Right now, we're sampling from the top of the rivers and canals. We're just having our sampling people go out and collect it from the bank. But we're talking about utilizing the intake structure at the Kissimmee ASR well pilot program so we can sample more representative of where we're actually going to pull the water. Because it's our understanding the PFAS may concentrate at the surface and not be as concentrated a little deeper. Long answer.
No problem at all. Our next question from Don Chappell. If water levels are artesian in the aquifers, where is the VADOS zone for ASR in these formations?
Georgia. The recharge for the upper Floridan is in the northern part of Florida and up into Georgia. So, and the Avon Park permeable zone, I'm not 100% sure where that daylights. There is in northern part of Florida, there is a town called Avon Park. So I'm guessing it probably daylights up in that area. So the Ocala and the Avon Park both come to the surface in the northern part of Florida and then up into Georgia. In fact, Georgia, the upper Florida aquifer is one of the primary aquifers for the state of Georgia.
Great. Next question from Ray Talkington again. How often will the ASR wells need redevelopment?
Another very good question. And I would guess for the upper Floridan, we're going to have more of a situation where we're going to have to rehabilitate those wells on a more frequent basis than the Avon Park permeable zone, just because of the size of the flow zones. We've got the fracture flown in the APPZ, and then we got the intergranular porosity in the upper Floridan. So the upper Floridan, since these wells aren't running constantly, we're going to be injecting water into them maybe 4 or 5 months and then storing it for 3 or 4 months and then pulling back out. I'm hoping that these wells will be 3-4 years, maybe even longer, between rehabilitation events, which is acidation for the upper Floridan, and then maybe 6, 7, 8 years for the APPZ. In fact, we have an APPZ ASR well over at L63 North that was installed in 1989, never been rehabbed. We pumped it at 10 million gallons a day, and we didn't pull the head off that well down to ground surface. So it's never been rehabbed, and it's still producing tons of water.
Another question from Tony Junta. And Tony, I apologize if I'm mispronouncing your last name. What constrains the injected water? As you inject water, why doesn't it just discharge somewhere else in the hydraulic system?
It will. And gradient, a lot of that is permeability and gradient. So for the Avon Park permeable zone, we do have some concerns about storing water long-term in that aquifer. And since these systems are designed to be wet season, dry season, if we can maintain that kind of a pattern, then we should be able to recover that water even from the APPZ at those high transmissivities. The model is going to help us understand that better. But as that water remains in the aquifer for a longer and longer period of times, it will migrate. And that's the case for any ASR system. So, for example, if we have a very prolonged wet season, we may add water to these aquifers for a long period of time, and then it might be 5-6 months before we hit the dry season. So we're going to have to manage that very carefully so that we're not wasting money but also just removing water from the system, even if we're taking it out, and that's over a longer period than 5 or 6 months, it's still helping the overall Everglades because we're removing nutrients, removing excess water that is affecting the estuaries. So there's still a benefit for taking water out, even if we're not recovering it at the same rate. So hope that answered the question.
Yeah. Question from Russ Patterson. Generally speaking, what kind of costs are involved in a project like this?
They're fairly expensive. These wells, for one UFA, one APPZ, and a dual zone monitoring well, which is completed to the same depths as the deepest wells, we're looking at about $11 million, 11 to 12 million. The treatment plant, 50 MGD treatment plant, I'm sure some of you on the phone here have worked on those, but it's 160, $170 million for a main membrane plant. And this plant isn't running 24/7 like most membrane plants. It's going to be shut down, 4, 5, 6 months out of the year when we don't need to be putting water in the ground. We're recovering. So it's going to be an interesting process for the district because they're not used to running plants, but also to have a plant that's going to be cycling on and cycling off. Now, a nice side effect of all this is once everything is completed out here and everything's restored, this could be a very large regional water supply system because there's going to be 275 million gallons of treated capacity out here. And the only thing that would need to be changed is doing chlorination or something to get it into a regional water system. So there's a future benefit to all this other than what's being done right now.
Excellent. Andy A asks if you're modeling using ModFlow, and also how do you determine the aquifer recharge zones?
Well, the aquifer recharge zones are outside our model domain. We're doing what's being called, and I'm using air quotes, a local scale model, even though it's pretty large, but we're not modeling all the way up to the recharge areas. So we're building on models that have been developed by South Florida Water Management District, which has very sophisticated models, all of the districts do, and and Corps of Engineer model that was done for this project. So we're piggybacking onto those, and our domain it doesn't extend even up to Orlando. So it's very local scale. Right now, it is concentrating or focused on C38 North and C38 South. So those recharge zones don't directly come into effect into the model. It's handled with a boundary condition.
I'm going to maybe pick two more questions here. We have several, but we are running short on time. So I'll pick one here first from C. Rich, who asks if, in addition to raising water levels in the lake with the injected water, whether or not there's any interest in evaluating the feasibility of storing the cooler injected water for summer heating purposes or heat transfer purposes.
Well, that has not been something that has come up. I don't know if Florida has a lot of that hydrothermal heat or cooling processes. I haven't run into too much. I used to live in Ohio. We did it all the time up there, but that has not been part of the discussion. So.
And then I think the last question here from Derek Holum, curious if you've considered using derivative analyses of the pumping test data to evaluate groundwater flow characteristics and aquifer boundaries.
That is something that we are doing, and that is being done by our modeling group right now. And something else that I failed to mention, we have so much data. If you think about it this way, that we did 8 5-day tests. I mean, most of us do one, and maybe we get a 5-day test. Most of the time it's 48 hours or 24 hours, but we have 8 5-day tests. There's so much data here that we cannot analyze it all in the time frame that we have to get it done. So there's PhDs, there's master's opportunities here with this data. The district is looking into that to try to spread the wealth a little bit, but also have people look into this more detailed. Even this fracture trace analysis that we're going to do, that is going to probably be expanded as well. So like I said at one point, this is data driven. There are so many stakeholders that everybody wants to understand in the minute details on what's going on out here, because we don't want to have any unintended consequences. So yes, we're looking into that, but there's more that can be done with the data that's being collected.
Well, I know we didn't get to every question. I do apologize for that. If it's a really pressing question, if you want to send that directly to me, my email address is awj@aipg.org. I'll try to make sure I get that over to Rick and see if he can give us a little bit of an answer. A second thing, very quickly, if you are on the webinar and you want a certificate for CEUs and you're outside of New York, that certificate's generated automatically as long as you are on the full webinar. It's only people in New York that have to take that quiz. So if that wasn't clear, I do apologize. Next month, at the end of March, Stephen Stokowski is going to be talking about the adaptive reuse of quarry pits in Boston as part of our Lunch and Earn series. So please, I hope that you will come and tune into that. Otherwise, I thank all of you for attending today, and Rick, especially you for sharing your time, energy, and expertise with AIPG and all of our members.
You're welcome. Enjoyed it.